All right, so we are talking about contaminant transport, and if I go back, I've recharged my pad, which ran out of juice last time, and you'll recall that this is the system we're looking at. So we made the point that to look at transport in these systems, we know how to look at this kind of plug flow through the system. That gives us exactly what it looks like in the core and what it looks like as it comes out. Actually, this is the equation that you're using. And last time we went into a bit more detail to talk about the behavior within the core, which would allow us to consider really whether it has to be this sharp front, which isn't always true. And we made the linkage, I think, that we can describe the behavior in terms of an equation that says something about this behavior. And if we look at the individual terms which make this up, then this whole thing on the right is mass in minus mass out. Equals accumulation, mass accumulation. Part of it is due to dispersion and diffusion, which are these two parts. One of it along the core, which only exists in a core. There is no lateral transverse dispersion. And if you allow different concentration gradients across the system in a 2D or a 3D plume, if you like, then this comes into play. So this is dispersion. And this is advection, physically being carried with the water, just like you're doing in assignment number 4, which is this mass flux here, which is advection. We made the comment that these dispersions are kind of pseudo-diffusions, and we use Fick's law. And they're kind of pseudo-diffusions because we represent them by a dispersion coefficient, which includes something that relates, so let's do that as longitudinal. So longitudinal dispersion coefficient is equal to longitudinal dispersivity, which is a coefficient that describes our aquifer, multiplied by the advective velocity maximum in the direction of that flow, the maximum one in this case, plus the diffusion coefficient multiplied by some parameter that corrects for the fact that it's flowing in and out of the pore space. So these two terms matter depending on the material we have. And if we look at materials which are, say, clays, low permeability materials, or sands and sandstones, which are high permeability materials, then this expression naturally takes care of itself. If permeability is high, then advective velocity is high, and therefore this term dominates. So dl is approximately equal to alpha L VA. And in the opposite case, if permeability is low, then advective velocity is low. This term would drop out, and dispersion is roughly equal to this diffusion, the same rate at which you smell aftershave wafting across a room or in water, moving in water, and multiplied by this. So that automatically gets taken care of. If the velocity is 0, this is the only term that exists, and so the only term appears. If velocity is high, then this term is large, and this is inconsequential, and so we can use that to represent this. This second order PDE is something that allows us to look at diffusion like problems, which we explained last time in terms of Gaussian distributions, etc. And this is the bulk motion downstream. So what we'd like to do is we would like to use that somehow. And so the other way perhaps for us to look at this, not so painfully, is to go here. So this is the same deal. This is the same stuff we've just gone through. So what I just talked about now is this. So you have that. Accumulation in... We mentioned these questions last time, if it's bright enough to see. If we're looking at this concentration as it goes downstream, if we have the front here spreading, then the question is, can we always get the location of that front from the velocity of the advective velocity? And we'll answer that question today because we have the tools to do that. And will it always be that this concentration is equal to the maximum concentration upstream? You can imagine that if it goes downstream in a tube, then it's confined and perhaps it would keep that high concentration. But if it's allowed to spread laterally, because you have lateral gradients, dc, dy, then as the stuff moves out to the side, you have less material dissolved in water that's contained within this zone. And so you might expect that this peak amount might diminish. So what we're going to do is we're going to go back to this expression, and I guess I can play around with this. I noticed this is from February the 9th, 2003. So this is exactly the same expression that we had last time. So I'm going to draw those back in. So that's the basic expression we have. What we're going to do is we're going to want to solve this. We're not going to solve it. We're going to use some standard equations. But those standard equations come in some form which, just like dimensional analysis in fluids, if you work out what the dimensionless variables are, you can get a solution to it, which is kind of a universal solution that will solve for every single combination of properties that you have. So what we could do is we could divide this through by an upstream concentration. So these are all relative concentrations, like this. And then we can look at this expression that we were going to solve and figure out what the terms are that are present within it. And so we could write this. We'd like to solve for the relative concentration between 1 and 0. That's all that is. And it would be defined in terms of the properties that describe it. One is longitudinal dispersion. If we're looking at one-dimensional flows, which is what we're doing in this, just flows along a tube, just as a... Then by definition, the concentration in the y direction equals 0, right? So in other words, if you fill this face up with exactly the same concentration all the way across it, it will move down here at that same concentration. And so the concentration as you go laterally is 0, so we get rid of that term. And we can look at the terms that control it. One is the longitudinal dispersion, one is x, one is the velocity in x, and one is time. So those are the 4 parameters that describe what we're doing as a function of this other dimensionless parameter. So we know what the units of these are. Well, you might not know what dispersion is. It's meters squared per second. You could figure it out from this equation in terms of the units, but we don't need to. Velocity is length over time. Time is time. Distance is in length, meters. So we have meters and seconds here, which are 2 out of the 3 parameters we could possibly have. This would be kilograms per meter cubed, mass per unit volume, but it's mass per unit volume divided by mass per unit volume, so it's got no dimensions. So we only have these. And Buckingham Pi says that if you have 4 variables and 3 mass, length, mass, length, and time, 2 of those left in there, then the total number of non-dimensional parameters you have is 2. So we know that we're going to have that. So we could take this equation and realize what parts of it are written in terms of non-dimensional components that we don't have to worry about, which would be those. And if we write this in terms of the remaining variables, this is 1 over time. This is dl over x squared, which is here. And this is velocity divided by x. So that's the way that we start with this. So how could we make this non-dimensional? What we could do is we could divide or multiply everything by time. So by definition, actually here, if this is in non-dimensional, then these also must be not dimensional anymore. So we end up with a couple of different things in our system. And we can always take this, this term here, and we can split this up into a non-dimensional term, which would be dispersion, time, x, and x, and multiply both. If we can multiply this both upstairs and downstairs, numerator and denominator by velocity, and we get this expression here. And so if I take out the things that I've just marked here, it will be quite apparent that we have an equation that's written in terms of two variables. One is this. This is called a Courant number after a well-known mathematician. You can't read that. I think the Courant Institute at New York University is named for him, a well-known mathematician. And it's the advective velocity times time divided by the distance downstream. And the other one is going to be this second term here. And I guess all I'm doing is, you note that this is one of the variables. This variable doesn't seem to conform to them, but if you multiply velocity top and bottom and then separate it out, you end up with this term, which we already have here, but also an extra non-dimensional term, a product of 2 non-dimensional terms making a single non-dimensional term. And this number is called the Peclet number. I think it's got a acute accent on it, which is dispersion, we've called it dl, divided by advective velocity times length. The Peclet number, actually, like all of it, well, this is a veritable trip down memory lane for 303, is a non-dimensional parameter. This is the Peclet number. It's the ratio of advective flux to dispersive flux, just like Reynolds number is inertial force to viscous force in our system. And the bottom line is that if we want to solve this equation here, which looks like it has lots of nasty variables in it, we can get them purely as a function of these 3 variables. The Courant number, which is this, the Peclet number, I'm going to write them out. We can get them as a function C over C not doing very well. Function of the Courant, I guess the Peclet number first, which is advective velocity times x over dispersion, and the Courant number, which is velocity times time over distance. And so this term here represents whether, actually, yeah, Peclet number PE goes to 0, for V goes to 0, and D omega. So we talked about these terms here being two discrete terms. When the velocity goes to 0, this term dominates, d star, or d star, I guess we called it d star, didn't we? D star was d times the product of this. It's dominated by this. When Peclet number is greater than 1, then dispersion is approximately equal to alpha L V A. So that's what's important for this. So these represent the case when advection is dominated or not. And so we, it's not on this plot. And for the Courant number, if we think about it, it's called velocity times over x. Velocity times time over x. This is also equal to, since advective velocity is equal to Darcy velocity over porosity, then this is equal to Darcy velocity times time over x times porosity. And in the stuff we'll use, we'll call this T sub r. And this is a pore volume. And so if you think of our system as being one where the concentration has been taken downstream so that it looks like this. This is C over C0. This is X. Then when one pore volume of the core, so if, in other words, the pore volume of the core will be the volume of the core multiplied by its porosity. So when one pore volume of fluid has entered the core, the tip of that pulse of water will be exactly at this end. And therefore, if it's carrying the pulse as the dissolved fluid and it's plug flow, then this plug flow front will be exactly at the end of this volume. So the Courant number, which is TR equals 1 pore volume. So in other words, if you had a core that was looking like this, and you put in 1/2 a pore volume of fluid, where would you expect the front to be if it was here? You expect it to go exactly half the length, right? This is TR equals 1/2. This is TR equals 1. This is TR equals 0. And so when it's gone one pore volume, it will look like this. And so that's just a useful metric for us to use in solving these equations. So that's about as simple as I can make it. I don't know whether it's been simple, but the point is we can solve this equation. We're not going to solve it. We're going to use some solutions. Those solutions will use these two variables because it's the minimum number of variables that you can get away with that characterizes it properly. And we'll use those to be able to say exactly what we think the plume will look like as we go downstream. So this is it. I guess we didn't say what we're going to do. And so what we'll look at is in terms of flows in both 1D and 3D. Skip 2D. It's kind of included. Don't need to do this. We've derived advection-dispersion equations. I don't think we need to look at that. I think we know what residence time distributions would look like. If we have plug flow, when it comes out of the core, if the Peclet number was high and dispersion was 0, we'd get this very sharp front. As this progressively grows, this front will be canted progressively further over in the residence time distribution. So I guess what we'd like to be able to say is something about exactly what this green curve looks like, and when the green curve might look like the red curve. So what we can do is we can take a core, we can describe a coordinate system that goes down the length of it. We can take the equation that we want to solve, which you've seen. It's derived in these terms that are not non-dimensionalized yet. And what we're going to do is we're going to have a constant concentration on the upstream, and that can be carried downstream by some advective velocity. And we would look at the concentration profile in space as we go in the x direction for different snapshots in time. And I guess we could also look at the residence time distribution when it comes out at this compliance point at the end. So it can either look like what the plume would look like along the core at a snapshot in time and in space, or we could look at how the residence time distribution comes out at the end. If we solve it, we end up with a not so straightforward expression, but one that describes our system. We talked about the complementary error function last time. It's an integration of the bell curve Gaussian distribution. You'll see that it has the parameters that describe our system. This is the length downstream. We've called this x, I guess. The advective velocity, the time at which we want our solution, and the longitudinal dispersion. And there shouldn't be any other terms other than those in this particular case. We could divide both sides through by C0, and we get rid of this term here. This would just be 1. And if we wanted to play around with this, or indeed, if we wanted to write this equation that we solve in terms of its dimensionless variables and solve it, we'd end up with this same solution. And this is the solution in terms of these other variables. So you remember in this case we have three variables. One is relative concentration. One is the Peclet number, which is the ratio of advective to dispersive fluxes. And the other one is this pore volume, which is equal to 1 when a pore volume has completely flushed the core down to the point where you're measuring it, and it's given by advective velocity, time, and length. And so if we plot this, I won't plot it, but if we plot it, you'll see this expression. I know you haven't bought Fetter, but this is out of Fetter. So this is what these curves look like. So this is one pore volume, right here. This is representing this. I shouldn't draw it. I don't know where to draw it. I don't really want to draw it here. Well, I guess I could draw it here. I will draw it here. So this is one pore. Actually, that's perhaps not a bad way to illustrate it. So this is the length of the core. This length in x would be this. This length along the core would be L. And so what we're doing is we're measuring the relative concentration at this point L. And this is the relative concentration, how it builds over time. And what you see, importantly, is that if the Peclet number was equal to infinity, then this curve would look like this. So this is Peclet number equal infinity. And so that's our classic plug flow system. It's moving, there's no dispersion ahead of it, And so it's just moving as a sweep, and it's ending up, the water behind it is holding stuff at equal concentration. But when you look at Peclet numbers which are progressively smaller than infinity, then this is for 100. This is for 10. These different curves are for a bunch of different boundary conditions. But if you take the solid curves, it's for the equation that we mentioned. And if the Peclet number is equal to 1, which is this one, then it means that if we're looking at the concentration at this downstream location, even at time 0, after we've just started doing it, we get some breakthrough at some low concentration. And the reason for that would be, I guess if we drew it on that the diagram, is that if you look at these, I can draw it here just as easily, is that we have this behavior where we have the core, it looks like this, concentration along the length of it, and the boundary conditions that we apply at the upstream end. We've drawn this figure before. C over C0, this is 1, this is 0, this is time, and we just turn it on. Won't do it. Why won't it? I don't know why it doesn't do that. I was just going to copy it and be very smart, but I can't do that. The concentration at the downstream is going to look like this. Again in time and relative concentration. And again, it would look like this after it breaks through. And in here, it would look like this. I think we used the other color scheme, red and green, were switched last time. So if this was plug flow, this would be it moving downstream. And I suppose the question would be, if the velocity is equal to 0, what would that plume look like? Well, the plume, if the velocity is equal to 0, can never actually get carried by advection. There is no advective velocity. And so the distribution of that would be at different times. It would look like this. T1, T2, and T3. And so merely making the case that if you look at this, at early times, this is before, so this is as the pore volumes are, well, let's choose a different number, at half a pore volume. So this is saying that if the Peclet number is equal to 1, at half a pore volume, then in other words, it would have swept like this. The concentration, in this particular case, I guess I'm going to get rid of these. Now I'm going to draw below it. So if the Peclet number is equal to 1, then that means that at half a pore volume, the concentration at the end point is equal to about 0.5. So that means that water would have traveled halfway down the core. But even though water has traveled halfway down the core, the concentration at this far end is equal to 0.5. And so that means that the plume, I suppose, would look something like this if we drew it beyond there. And I guess the question is, why is the material reaching the end of the core if one pore volume, only half a pore volume has only gone halfway down the core? And I guess probably the explanation for that is that we could describe the behavior as looking like, if you draw the core, it would look something like, I don't know what our color scheme is anymore. You could imagine these fingers reaching downstream being something like this. So if this was our water that's contaminated, C over C0 is equal to 1. Then if you take a section that's across here and sum up the portions, this portion would concentration 0, this would be 1, this would be 0, this would be 1, this would be 0. And so maybe on average, the concentration as you get to the end of here is equal to 0 times 0.2, which is the volume, 1 times 0.2, 0 times 0.2. Just a volume-weighted average. 1, 2, 3, 4, 5. And I guess on average for those, it would actually be 0.4. So that's a better way to explain what's going on. So the reason this works this way is that you get these premature breakthrough, even though you've only put in a volume of pore fluid equal to half the length of the core. The effects of it are felt downstream, because in the high velocity channels you get stuff moving ahead of it either by advection or by the process of molecular diffusion. If the velocity of this is very slow, for instance, a thought example is if the velocity in the core is 0, if you're relying on advection to carry it all the way to the end, it will never arrive there and the concentration will always be 0 down at the bottom. But if you have diffusion operating, so it very slowly diffuses along the length, then it will arrive at the bottom at some long time in the future, given by a small number of pore volumes, I guess. So the figure that you saw drawn on here, at the bottom of that figure, is this. So it merely says that the residence time distribution as it comes out, if the Peclet number is large, will be plug flow, and therefore you can use what we've done before, that velocity is equal to length over time, and therefore length is equal to velocity times time, or time is equal to length over velocity. And so this is equal to the time taken for one pore volume to come through. We've used a different unit. And so this would be T is equal to length over velocity. So in the case where you have plug flow, then you exactly have that, and you'd be able to calculate the from the half concentration would be present at that location. But when the Peclet numbers are progressively smaller, for 100 it's still pretty true. So Peclet number, let's see on this. So if you wanted to be able to predict whether you could use. So one useful metric would be to say that the mean concentration of 0.5, which is this line going through it, is present at the location of one pore volume. That's certainly good for Peclet number of infinity. It seems certainly good for a Peclet number of 100. It seems not too bad for a Peclet number of 10. It's off by this amount. But for a Peclet number of 1, it's nowhere close. And so we can use the Peclet number of an index for how well we might want to use our solution. And it's drawn here, right? So it doesn't work for Peclet number of 1. We'd have to use this full expression that's at the top of the figure to calculate that. But if we want to use it for a Peclet number of 10, infinity 10 or 100, anything bigger than 10, it seems that this prediction for the time it takes to get downstream to 50% concentration is about right. We don't really know exactly how canted over this curve is. It's not vertical anymore for progressively smaller and smaller Peclet numbers, but this estimation might not be too bad. If the Peclet number is smaller than 10, then maybe we need to use this curve. And so I guess we just need to be aware of when our simple characterizations can work for us and when they can't. And so we now know that. There are a couple of other solutions. So the fact that there are a bunch of curves on this curve, so if you look at this rather messy curve, for Peclet number of 1, the solutions are this curve here, and this curve here, with all the hashes joining those. All those three curves are for different boundary conditions for solving this one-dimensional problem. So the first boundary condition is where on the upstream face you put a concentration at time 0 and you hold that concentration constant. The second one is where you put a concentration, you inject a volume of that water containing that concentration at time 0 and you keep on injecting it at that upstream face. And the third one is where you have, what was this one? That was the second one, constant concentration. And the third one is when you have slug injection. So instead of having this heavy side function where it starts at time 0 and keeps going at the same concentration, this one you actually spike, push something into the system, then turn it off. And so that's why you would think in this case that the concentrations at arrival would be the lowest concentrations. So in order for each of those injection cases, this is the one constant upstream concentration, this is injection at constant rate at that magnitude, and this is for the slug, so-called slug injection. Because you inject a slug and then you don't inject it anymore. So we have those expressions for those and we know what they look like. That's enough. So the next thing we could do is we could look at the behavior in 3D. And so this is actually going to mimic exactly what we had before. Remember we had this figure that looked like a cross-section through an aquifer. That was this. Yeah, well, correct.
Just curious, why is there the example for a fixed step function in a plastic solution? Like, wouldn't a real life scenario you just have continuous injection? Like, what's the purpose?
It could be where you have a small volume that gets placed in the subsurface. It's all present in dissolved form, and that dissolved cloud gets carried downstream. Or it could be that it's a very small volume, and once it's dissolved out, then no longer you have a source that's continuously dissolving at some low concentration, like in your assignment 4, right?
Thank you.
Yeah, no problem. And so this, we drew this, and we had this picture of a plume. Actually, I'm going to do it slightly differently. So actually this addresses exactly that same question. So if you have a plume that's continuously dissolving and there's a big volume that continues, the gift that goes on giving, continues to supply dissolved components into the water as it goes downstream, then you'd expect the plume to look like this. If conversely you had the system where you had a plume that started off here and was carried downstream, then just like a puff of smoke in the atmosphere, I guess, you'd see that it would move downstream and it would spread and it would get progressively larger. This would be time 1, this is time 2, and time 3. This actually is just time 3, perhaps. And these are contours of different concentrations. This concentration would be the smallest. If we drew a profile of concentrations along the length, then this would look like this, right? Just going along the length. If we drew, we did this as well before, right? If you drew a cross profile across a portion of this, then this is what the concentrations would look like. C0, I guess this is Y. This is X, and this is C0. And so if you imagine it's dropping a pebble in a moving stream, actually not a very good example. It's smoke coming out of a smokestack. Comes out, has some initial concentration, it's quite concentrated. It diffuses and disperses with time, but it also gets carried downstream because there's an advective velocity that carries it downstream, and it gets wider and wider as it goes on. So if we come back to the analog of a beaker with a drop of ink in it, this is the drop of ink as it goes in. This is if you wait for 10 minutes. This is if you wait for 20 minutes. It spreads out. Each of these, I guess, would look like this would be this. This would be this. And this would be this, right? This is the plume at time 1, 2, and 3, so it's the same plume. It doesn't exist at, it exists at 3 different time facets when you take a picture of it. And so this is just what's going on. It's the same as our diffusion if we have a drop of ink and it diffuses. All that's different is that it's being carried down at some kind of velocity, and this velocity is the advective velocity. If we know that the velocity is equal to length over time, then length is equal to velocity times time. And so this would just be the velocity times time would take it this far, L1, and the velocity times time would take it L2 and L3. And so all we're doing is if we have this solution, which is our Gaussian distribution, like the grading curve that gives us this behavior, all we need to do is translate it downrange as a function of time. And if you look at the solution for that, it would be the same things that would have been used in Lubitsch's atmospheric dispersion class. And that is that this is the solution for a Gaussian distribution. And all that's different is that it starts off at some location, x0, y0, at time t0, and it moves down at some velocity, and the length it will move in time is going to be the product of velocity and time, so it'll get to this point in time. So if you attach your coordinate system to that plume and just translate that coordinate system downstream, this uppercase X, Y, and Z vertically, I guess. Then if you have the solution for the bell curve as it goes downstream, all you do is translate it. And so the solution for this is just this, the bell curve solution being physically translated downstream, and you see you have the same terms that are represented. You have a mass of solvent or mass of material that is put in place. This is the product of concentration times the volume of water. This is time. These are the dispersion coefficients. So I guess if you have something going down gradient, it would have a longitudinal dispersion coefficient, which we'll call dx. You would have a lateral dispersion, transverse dispersion coefficient, which we'll call in this dy. And I guess it would have a vertical one, which we have no analog to that, which would be dz. So it can diffuse and disperse in all directions according to some coefficients which represent that behavior. They may all be the same or they may be different. And this gives its coordinates downstream as a function of time. And if you solve that expression and write it in slightly simpler form, you get the expression relative to this moving coordinate system. So this is where it starts off from. If you find yourself at time t equals 10 minutes, 100 seconds, then if the velocity is equal to 1 meter a second, then from velocity is equal to length over time, length is equal to velocity times time, then it would have traveled 1 meter a second times 100. Ridiculous velocities in groundwater equals 100 meters. So the center of your coordinate system would move downstream by 100 meters, and that would now be your origin. And now if you calculate what the plume looks like relative to that coordinate system, it would just be arranged as a bell curve relative to that location. And that's what this expression is here. So we're just making it simpler by realizing that this term here represents how it migrates downstream. I guess the y and the z will always be on the same straight line, right? If it starts off at y0, the location as it moves downrange will also be on centered on y0 and on z0 out of the page. And so the solution will just be relative to these moving coordinates, which are just migrating downrange. So it's useful to do that because if we do use these migrating coordinates, it turns out that we can calculate what the maximum concentration in the middle of the plume is just a function of the total mass that was put in at time 0, which is conserved. At time 0 or at time 10 minutes or 100 years, it's still the same mass that's in the plume. And then just divided through by time. So as time gets larger, the concentration will be reduced because it's in the denominator, and these terms are constant. And so what you'd expect that it looks like, is exactly what we drew before. So this would be C over C0. So I guess initially it would look like this. And this here is C max. As you go down to here, it would look like this. And as you go down to here, and each of these would be C max. Right? And I suppose if you think about this, you know, the area that's under each of these curves is roughly the same, because it represents a concentration multiplied by a volume. You know, this length here is this length is a length, but if you take the length in all directions, it's kind of a volume. And so if you think about the same mass being included in the plume at every location, if you integrate the areas under these curves, it represents the total mass that's involved in this plume, nothing more than that. And the more interesting result that comes out of this is that the limits of this plume, so if you look at the limit of this plume, 3 sigma, this is 3 standard deviations. So we said before that the bell curve is a normal probability distribution. A standard deviation says how wide that is. And you know that, I can't remember what it is, but I think 3 standard deviations means that at 3 standard deviations it contains, is it 99.7% of the area under this curve is included within the length, which is 3 standard deviations. Likewise, 99.7% of this mass is included in the portion of this which is equal to 3 standard deviations. So the utility of this is if you knew what a plume looked like in the field, and you knew that the length of this plume is equal to 3 standard deviations, which is defined in terms of this expression here. If you know the length, so in other words, if you know this length, which I presume you could get from measuring it, then if you know how long it is since the plume has been in the field, then you can calculate what the dispersion coefficient would be. So you could calculate from this the unknown parameter is equal to dl. Or alternatively, if you knew what dl was, 1 meter squared per second, and you knew that the time was equal to 100 seconds, and you knew that the velocity was equal to 10 meters a second, then you could calculate exactly how far downrange the plume had gone. So L would be equal to velocity times time. Which is 10 meters a second times 100. Thousand meters. And relative to that location, the plume which originated from this point here, the plume would look like this. I guess I've switched my terms. Let's call this X. No, let's not call it X. Let's still call it L. Let's call this the width W. So W equals 3 sigma equals 3 times 2 times 1 meter squared a second times 100 seconds, all square root, right? So all we're doing is plugging something into this. This is what we're calling W now, which is the length of the plume. So no, it started off here at time 0. You know from advection that it's traveled down range. I didn't write it down. 1,000 meters. So it's traveled downrange 1,000 meters, and this is the center of mass of the plume. And relative to that plume, the length of it, upstream and downstream, is a total which is equal to 3 times square root 2 dl times time, which is this term here. And actually, the W is equal to this length here. It's this upstream length. This is 3 standard deviations. And so if we have that information, we have the ability to calculate exactly what our plume will look as we go downstream. So that's it. So when we get further, we'll talk about how we can use that in some useful way. And I won't talk today. This is an experiment that was done in Ontario, where it was done exactly what we're looking at. So you intentionally put into the ground an amount of fluid which is exactly this delta distribution that exists at time 0, and as time from 83 days to 460 days to 647 days, this plume progressively goes further down gradient. And so if you knew what the dispersion coefficient was for this aquifer, and you know the time you put this in, and you know the advective velocity of this system, you'd be able to calculate from putting this stuff in the system at time 0 exactly where it would be at 462 days, and exactly what it would look like in terms of its length from just using what we've talked about in this last part here. So we take advantage of the fact that this distribution is a normal probability distribution. It's defined in terms of a standard deviation and a mean, and we can use that to calculate the shape of the plume, as it turns out.